perhaps, among other things, the Tacoma Narrows Bridge was the most spectacular Aeolian harp in history. Unfortunately, its first performance was destined to run only about 4 months. In the meantime, she was a beautiful bridge. Beautiful, but a little strange. Even before construction was completed, people observed its peculiar behavior. That was because, even in a light breeze, ripples ran along the bridge. After a while, one of the local humorists called her Galloping Gertie. And for fairly obvious reasons, the name stuck, at least until the 7th of November, 1940. Then as now, Seattle and Tacoma were sports-minded cities. For 4 months, a regional sport was to drive across the bridge on a windy day. While some claimed it was like riding a roller coaster, others found it a little disconcerting to see the car in front disappear. How popular this bridge sport was, or to what extent it might have spread across the country, is anybody's guess. On November 7th, 1940, the winds were relatively moderate, about 40 miles per hour. A new mode appeared. Rather than ripple, the bridge began to twist. A wind of 40 miles per hour is not too strong, but it was strong enough to start the bridge twisting violently. And at 11 a.m., it fell. Investigators were mystified. A bridge constructed according to the best engineering standards of the day, perhaps the best bridge in the world. This was not a bridge that was supposed to collapse. What in the world had happened?
So the engineers were mystified. I'm mystified that the engineers were mystified. And what happened to the bridge, it just simply resonated. Intuitively, you kind of know why the bridge kind of collapsed, but let's just solidify that understanding. Okay, guys, how fast the wave travels depends on the medium itself. So speed of the wave is going to depend on the tension of the medium, tension within the medium or the medium itself, and it's going to be related to the density of the medium itself. All right, so the larger the tension is, the faster the wave is going to travel, and denser the material is, the slower it's going to travel. All right, if tension increases like 10 times faster than density, which means that the wave is going to travel much faster in that medium.
In Asia and other parts of the world, rocks have been used to make music for centuries. Lawrence Liven is the curator of musical instruments at New York's Metropolitan Museum of Art.
These stones, which are very brittle and hard internally, are the ones that ring best. And I think people discovered this ringing property by accident. They didn't set out to look for rocks that sounded, but probably accidentally, by knocking against things, early people realized that some of these very hard stones were more apt to make a pure tone than the soft sandstones. And so when people wanted to make instruments out of rock, they began looking for the hard materials, probably formed by volcanic forces.
The museum's collection includes a very whimsical rock instrument.
This is one of my favorite instruments in the whole collection. This is called a rock harmonicon, and it's really a kind of xylophone, but instead of wooden slabs, it's made with stone slabs. Each rock is individually shaped by chipping away the edges and the bottom underneath in order to make it sound the right pitch. And once it's been chipped away and the right pitch has been found, it never has to be tuned again because the rock is very stable and it's not affected by humidity or temperature. So it's in tune and will stay in tune forever unless we drop one. It came into our collection about 1890 when it was left here by a family named Till, who were English musicians who performed in the music halls and vaudeville stage.
Long before the Beatles or the Rolling Stones, the Tills were advertising themselves as a rock band.
Okay, a couple of things which are interesting.
In each rock, out of rock, they began looking for the hard.
Okay, now all these rocks are identical in every single respect. They'll have the same tension within the rocks and they will have the same exact density. And not all rocks sound the same.
Instrument.
Which means that all of them have different frequencies. All right, so what is that frequency? Frequency is the number of cycles per second, or number of vibrations per second, right? So why is it that the frequencies are different, given the fact that in all these rocks, the disturbance is traveling at the same speed? All right, so they all have identical structures, molecular structures. Tension within the medium is the same. The density of the density is the same. So which means that in every single rock, disturbance is traveling at the same speed. The waves are traveling at the same speed, yet the frequencies are different. And they get to control what these frequencies are by changing the shape. And so evidently the frequency is directly related to the shape or the sizes of these rocks that we're looking at. So the question is how? Okay, guys, what's the frequency? Frequency is number of vibrations per second, the number of wavelengths per second that you're looking at. These are known as resonant frequencies. This is known as the fundamental frequency, the first harmonic, whatever that is. It's going to become fairly obvious shortly. You can double it, you can triple it. These are known as natural frequencies. So for a given density as well as tension of the materials can vibrate at their natural frequencies determined by the characteristics of the medium. This is the lowest frequency at which you can vibrate. You can double it, you can triple it. All right, so the lowest frequency is known as the fundamental frequency. All right, and then you can double that frequency, and then you can triple that frequency. All right, so these are known as the resonant frequencies or the natural frequencies of a system that we are looking at. All right, so what determines the frequency that you will hear? It determines a couple of things. Number one, this is the length of the structure that you're looking at. Imagine that this is a rock. So what's going to happen is the wave is going to travel forward and then come back to the same point. This is a single cycle that you're looking at. So the wave disturbance travels forward, hits the boundary, bounces back, comes back to the same point. This is your first cycle. All right, so this is a single cycle. This is your first cycle. All right, so if it travels forward and comes back to the same point, if it takes 1 single second, so your cycle is going to be 1 single second. So it's going to be a 1 single cycle per second, right? Now, within a single second, if it does this 20 times, now the frequency is going to be 20 cycles per second. It's going to be 20 hertz. Okay, so notice that the faster the wave travels, the larger the frequency is going to be, which means that more often it can complete the cycle. There's a single cycle, here's your second cycle, the third cycle. So faster the wave travels, the larger the number of cycles that it can complete within 1 single second, larger the frequency is going to be. That's what it is. Except the situation is this: in every single rock that you're looking at, every single rock tablet that you're looking at, the wave is going to be traveling at the same speed. It's going to move in the forward direction, and then it's going to come back to the same point. All right, so here's your single cycle that you're looking at. In every single one of them, it's going to travel at the same speed because every single one of them is going to have the same density. It's going to have the same internal tension within the material. But notice that if you make the length shorter, it's going to be able to complete that cycle sooner, so which means that the frequency is going to be higher. All right, so the length is going to matter, right? So this is the length through which the vibration is going to take place, through which the wave is going to travel. So shorter the length is, the more often it can go back and forth, the larger the frequency is going to be. So this thing is going to be moving in this direction. So the speed of this wave is going to depend on the length that it's going to travel forward and backwards. So this is the total length, and T represents the amount of time for that cycle to complete itself. So the total length divided by the total time is going to give you the wave speed. And you know how fast the wave travels depends on the characteristics of the medium, right? All right, so capital T represents the period of this motion. Reciprocal of the period is going to be the frequency, and sum for frequency, and then we end up getting an expression. So this wave traveling twice that length within a single second is going to be our frequency that we're looking at. All right, so speed depends on the tension of the material, so it's going to be inversely proportional to the density. And then we came up with a mathematical expression. All right, so this is going to tell us about the natural frequency of a system that you're looking at. Anything made up of molecules, atoms and molecules, will have their own natural frequencies. So the natural frequency of a structure is going to depend on the length of the material. So it's inversely proportional to it. So smaller the length is, the larger the frequency is. So intuitively, we figured that out. And the wave speed depends on the tension. It's going to be inversely proportional to the density. So we also knew that. The faster it moves, the larger the frequency is. And the smaller the length is, the larger the frequency is going to be. All right, so we got some common sense stuff out of that. All right, and you can double the frequency, natural frequency. All right, the first one is known as the fundamental frequency. All right, you can double it, so it's got to be 2 times the fundamental frequency. You can triple it, it's got to be 3 times the fundamental frequency. Those are known as the resonant frequencies of a system. These are the natural frequencies. So any system which is made up of atoms and molecules can vibrate at its natural frequencies. These are the frequencies at which it's going to vibrate naturally. That's what it means, which is going to be determined by the molecular density as well as the molecular tension of the material that we're looking at. All right, standing wave is, let's focus on the definition of it. It's standing wave is a stationary wave in essence, which means that either one end is going to be fixed or both ends will be fixed. Notice that this is vibrating at its lowest frequency, the fundamental frequency. All right, so this is the lowest frequency at which you can vibrate. You can double this, so you end up getting 2 times its fundamental frequency. You can triple it. Now you have 3 times its fundamental frequency that you're looking at. All right, fundamental frequency is also known as the fundamental, which is the first harmonic. You can double it. You can double the fundamental frequency, so this becomes the second harmonic. You can triple the fundamental frequency, otherwise known as the third harmonic. All right, so these are known as natural frequencies. Once again, I'm going to repeat it, also known as the resonant frequencies of a system. So the question is, what is resonance? Okay, so what happens when a system resonates?
This is your captain speaking. If I could have your attention for a moment, folks, I'd just like to say that American is proud to be the only airline to remove seats throughout coach, so you all can have more room to cross your legs. However, we do kindly request that you not all do it at the same time. Thank you.
All right, so what's resonance? You guys are looking at it. What's resonance? This airplane is resonating. All right, so what's the meaning of it? Guys, resonance is what happens when you match one of those natural frequencies of a system externally. What happens is it causes a constructive interference. As a result, the amplitude starts to get larger and larger and larger. All right, so the resonance is what happens when there are two overlapping waves and when they interfere constructively. All right, so what happens is the amplitude becomes maximized. Okay, in this case, this airplane has its own natural frequency or frequencies. Okay, it's got its own natural vibrations. And when these people start to shift their legs from left to right to left at one of those natural frequencies, that frequency becomes amplified. All right, that phenomenon is known as resonance. Good example of resonance is a child on a swing. All right, the swing is going to have its natural frequency. It's going to go forward and backward a number of times per second. It's got its own natural frequency. So when you match that frequency with a push, when you start reinforcing that frequency externally, what happens, the amplitude of that motion is going to keep increasing and increasing. So whenever you match the natural frequency or any one of the natural frequencies of a system externally, you get to amplify the amplitude of that frequency. And you can amplify that frequency to the breaking point of that system. All right, so that frequency matching, in order to increase the amplification at that frequency, is known as resonance.
Right? The time has come to break the wine glass. But I'm not going to do it with my own voice. My contract with the Met won't permit that. And there's another problem. This takes practice, and I only have the one wine glass. So I'm going to try it first using this ordinary laboratory beaker. Now here's how it's going to work. All of this stuff here is going to substitute for me and make a pure tone. That will make the beaker vibrate. And then I've got this microphone here, which is listening to what the beaker does. And the output of the microphone is on this oscilloscope, so you'll be able to see on the oscilloscope what the beaker is doing. Watch this. You see that? Okay. Now, what I have to do is to turn up the volume, and that makes the beaker vibrate. Now you can see that the beaker is vibrating, but not very much because it's not exactly at the right frequency. It has to be at precisely the right frequency, the resonant frequency of the beaker, in order to vibrate enough to make it break. So I'm going to tune this to the right frequency. There it is, right there. That's it. All right? Now all I have to do is to turn up the volume all the way up, and it will break the beaker. Okay, you ready for this? And the people in the first couple of rows, your ears will bleed a little bit, but don't worry about it. It's not serious. You ready for this? Here we go. So we managed to do it without ever breaking this exquisite wine glass. You see, that's why they bought it for me. They knew I'd never get around to breaking it. All right? That's it for today.
All right, so resonance is what happens when you cause a constructive interference between two waves. All right, in this case, you're matching one of the natural frequencies of a physical system, in our case, with an external frequency that matches it. And then what happens? The amplitude gets maximized to the breaking point of a system.
In the next 800 years, engineering passed from an art into a science, and the achievements and failures of engineers became true sway like...
And that's exactly what happened here.
Turbines out there.
So you got this
Park
bridge.
on a hill beside the bridge and watch it go up and down.
All right, so here's what's happening. There's wind going across the bridge at 40 miles per hour. Okay, so the wind is causing all these vibrations.
They let people...
And the vibrations caused by the wind, one of the vibrations matches one of the natural frequencies of the bridge. Now what happens, that frequency becomes amplified.
go when the dropping was so sudden that it felt like an old-fashioned... That
so
when the wind was go when the...
Put it off as a 4,000-feet ground break longer.
All right, so what happened to the bridge was it got resonated. Okay, so what's causing the resonance though? This is the surprising part. This is the reason why these engineers were really astonished. Because you got a wind which is moving across the bridge at 40 miles per hour, and causing all these vibrations all over the bridge. And one of those vibrations matched one of the natural frequencies of the bridge. Obviously, that particular vibration became amplified. So it became larger and larger and larger and larger. At some point, the bridge simply broke down. All right, so what's causing the vibrations of the bridge? Okay, guys, here's what's happening. Wind is coming from left to right, imagine. Wind is just a fluid. Fluid doesn't mean it's wet. It's just anything that flows is known as a fluid in this case. All right, when you force the fluid into a smaller opening, like water through a partially closed hose, what happens? The water is going to speed up. Wind does the same thing. So under the bridge, the wind is moving faster than over the bridge. Faster moving wind under the bridge is going to create a lower pressure underneath. Right, so the pressure difference between above and below the wing, the bridge is going to pull the bridge in the downward direction, and then the bridge bounces back up. Once again, the pressure difference pulls it down, the bridge is going to bounce back up. And all of a sudden, you get this vibration, up and down vibration. And then that up and down vibration at that speed, about 40 miles per hour, unexpectedly matched one of the natural frequencies of the bridge. So that particular frequency became amplified. So it's getting larger and larger and larger. You end up getting this swaying motion side to side, and then the vibration is going up and down. All right, so there's a natural frequency that's becoming amplified. And then
An old-fashioned elevator.
consequently, the bridge went down.
Like that.
Galloping Gertie remained open to traffic for 4 months, but in November, everybody was ordered off as a 40-mile-an-hour gale whipped across her deck, lifting the roadway like a sail.
We went out to watch it whip, and it was really whipping, and there was one car on it. But then it got late, and so we left.
By afternoon, the stresses were too much.
Over stream, every bridge ever designed.
All right, so the question is, how do you fix this problem so that it doesn't happen again? What is it that you have to do? Okay, I got news for you. There are a couple of things that you can control. Obviously, you have to change the natural frequency of the bridge while you're constructing it. It's done on purpose usually, okay? So that it cannot be matched externally. Okay, so you don't want to match the natural frequency of a bridge externally. So the couple of things that you can control the length of the bridge, obviously. The length of the bridge is going to be constant because it has to span a certain length, obviously. So that's going to be constant. You cannot change it. I mean, you cannot make the bridge any longer. It cannot be any shorter. You cannot make it any longer. Even if you were to make it longer, then natural frequency will go down further. All right, if you make the natural frequency low enough, you can match it externally very easily. So somebody's going to sneeze on the bridge is going to go down. So no good. All right, so the length is going to be fixed. The only other things that you can control is the mass of the bridge. You can make it more massive. Making it more massive is not going to help you. The more massive it is, the lower the natural frequency is going to be. Once again, guys, it can go down very easily because you can match it very easily if that's the case. The only other thing that you can do is increase the tension of the bridge, which means that make it more rigid, for God's sake. It's that simple. I mean, the first time you saw this bridge, did you feel that this was a safe bridge? Intuitively, you knew it wasn't safe. This bridge is not supposed to be swaying that much. It doesn't make sense. So the only thing that they realized that they had to do was just make it more rigid. Today's bridges don't sway like that. So you make it rigid, what happens? The natural frequencies will go up. When you increase the natural frequencies, there's little to no chance that you can match that natural frequency externally. All right, so this is also something that we use in earthquake-proof engineering. Okay, the buildings, whenever you build them, earthquakes have known frequencies, and then buildings are built in such a way that no earthquake frequency is going to match any of the natural frequencies of a building or a bridge. So these bridges and the buildings are made fairly safe. I don't know about your home or my home. If there's an earthquake, first chance I get, I would probably leave, just get outside, because I don't know about the buildings. But the commercial buildings, most of them are built to these specifications, so they should be fairly safe. All right, so that's what it is. Just make it much more rigid. When you make it rigid, what happens? The natural frequency goes up. And these are the resonant frequencies. So if there's no way you can match these resonant frequencies, you cannot resonate these buildings or the bridges, and they will be safe or safer. All right, so the best answer based on the discussion that we had is it's A, right? So you have to increase the natural frequency by increasing the tension of the bridge.